Good afternoon. Can you hear me?
Yes, sir.
Good afternoon.
Good.
Yes. So let us start our discussion. Okay. So we were discussing about thrust and thrust equation, and then some other we are going through some other definition regarding jet engines, and the discussion that is going on in this area is valid for any type of jet engine that we are going to study. So turbojet, turboprop, and turbofan engines. Okay. So we have already started discussing about turbojet engines in the previous couple of classes. We have seen what are the main processes in a turbojet engine, what is the structure, things like that, and we have discussed that the main aim in performing design calculations of a turbojet engine or any jet engine is to find out what is the thrust that is generated by the engine. Okay, instead of the power output, thrust is the more important factor. Although power also is an important factor, but thrust is the more important factor. Just a second, okay, please hold on for a second. So we have seen that there can be two components of thrust. Please ask me questions if you don't understand something, because this part is very important. So one of the major factors for thrust generation is the change in momentum. So this is known as momentum thrust, and we can write this as, in general form, this can be written as mass flow rate of air at the intake, m dot I, this multiplied by 1 plus f into exit velocity v minus vi. Okay, this 1 plus f. So this f factor comes because there is additional mass at the exit. Okay, so the combustion products have higher mass as compared to the inlet air because of the addition of fuel. Okay, so if we ignore the fuel air ratio as a very small term, you can simplify this as m dot I ve minus vi. However, for our problems or for design calculations that we are going to perform in subsequent classes or in the exam, you have to take this 1 plus f factor. You cannot ignore it. Only for this simple calculations that we have done, we are going to ignore this f factor. Otherwise, we should take this. Otherwise, there will be around 2%, 3% error in the calculation. Okay. The second term we have denoted it as pressure thrust. Okay. So what is the reason for this pressure thrust? We have discussed that if the jet engine has a convergent nozzle instead of a convergent divergent nozzle. Okay. So we have discussed something like this. So so this is from yesterday's class. If the nozzle is like that, convergent, so it only decreases in area. So at some pressure on the outside, at some ambient pressure on the outside, the nozzle will become choked, which means that the velocity at the outlet section will become equal to the speed of sound. And then it cannot be accelerated further beyond the speed of sound, because in a convergent nozzle, so if you want to increase the speed beyond the speed of sound, the speed increases, the velocity increases if you have a increasing area. But because convergent nozzle increasing area, so the velocity cannot increase beyond the speed of sound. Okay, so it is limited to speed of sound at this position. Okay, so this condition we call it as choked. If we had a divergent section beyond this point, then the velocity could have been increased beyond the speed of sound, and we could have got much larger velocity. But in most general jet engines, most cases, we have a convergent nozzle. We will discuss this, why this is the case later on. But let us assume at this moment that in most cases we have convergent nozzles. Okay, and in that case, once it becomes choked, and if you keep on decreasing the outside pressure, the pressure at this exit area or the throat section cannot decrease below the critical pressure. So there is a value for there is a particular value for the critical pressure ratio. So the ratio at the exit to the inlet is approximately equal to 0.5833 if this is air. You can calculate the ratio uh, for combustion products. This ratio depends only on the gamma value, and we will see also what is the ratio later on, but this only depends on the gamma value, and as a result this pressure depends only on the inlet pressure. So if the inlet pressure is fixed, the exit pressure is also fixed. Okay, so once you know what is the exit pressure, if the outside atmospheric pressure is lower than the exit pressure, there exists a pressure difference between this section and the outside section. Okay, between this point and the outside point, which causes a force pressure into area. So that pressure difference into area, delta P into area, causes a force on the exhaust gases in the downstream direction, which causes an opposite reaction on the engine and generates a thrust. Okay, this we call as pressure thrust. This is equal to the pressure at the exit section minus the far away ambient pressure, which is PA. So PE minus PA into area of the exit section of the nozzle, which let us call it as AE. Okay, exit area. So this is the pressure thrust. This will only exist if the nozzle is choked in convergent nozzle case. Okay, otherwise this will not exist. It will be zero. If the nozzle is not choked, P is equal to PA and there is no pressure thrust. Okay. In that case, only momentum thrust is present. In general, also momentum thrust may be much higher than the pressure thrust. These things we have discussed, and we have gone through some other terminology. What is gross thrust? What is inlet drag? And we have denoted one effective speed ratio, which is the ratio of the aircraft velocity VI or the inlet velocity. Remember that the inlet velocity is due to aircraft only. So if we assume that the air is static, because the engine is moving forward with velocity Vi, from the point of view of the engine, we see that the air is coming inward at a velocity Vi. Okay. So if you are sitting on the engine, you see that the velocity is Vi. Actually, the air is static outside to a static observer, and the engine is moving forward with a velocity Vi. Okay. So this ratio is known as effective speed ratio, and based on this, we have found an optimum power also, which occurs when the exhaust velocity of the engine is twice the inlet velocity. Okay, exhaust velocity is twice the inlet velocity. Then we have also defined some term called specific thrust, which is the thrust generated per unit mass flow rate. Okay, so if you ignore the pressure thrust and fuel air ratio, this can be denoted as V minus Vi. If you have the general term like this, then you have to divide the entire term by m dot I. Okay, to get the specific thrust. You cannot use this expression. Once you are calculating for your problem and you have both momentum thrust as well as pressure thrust, you have to calculate the entire thrust and then divide by m dot I to get the specific thrust. This also we have defined, and another important parameter we have defined is the thrust specific fuel consumption, which is the mass flow rate of fuel by the total thrust. This can also be written as fuel air ratio by the specific thrust. Okay. So towards the end, we were discussing about something called propulsive efficiency. So this propulsive efficiency we denoted as the useful energy that, or the energy that is actually used for moving the engine forward. Okay, this energy that is used for moving the engine forward, and this is different from the energy that is generated by the engine. Okay, let us consider the energy conversion in a two-step process. So initially what do you have? You have some chemical energy in the fuel. Okay, you have some chemical energy in the fuel, and your engine, what does the engine do? It converts this chemical energy, some part of this chemical energy, into work for the turbine, which is used for running the compressor. The rest of the chemical energy is used for generating kinetic energy of the exhaust gases. Okay, so if the engine has better efficiency, means if the conversion ratio is better, it will generate more kinetic energy of the exhaust gases. Okay, so this is one part of energy conversion. What is the second part? Now this kinetic energy that is generated for the engine, not we cannot use the entire kinetic energy for moving the engine forward. Only part of it is used for moving the engine forward, and the rest of it is gets lost to the atmosphere. Okay, it is just it gets converted to thermal energy. It gets dissipated as thermal energy in the atmosphere. Okay, so this propulsive efficiency takes into account the second part of the energy conversion. How efficiently we are converting the kinetic energy of the exhaust gases into the energy which is used for moving the aircraft forward. Okay, so how can we define that? Excuse me for a minute. Okay, can you hear me? Can someone confirm?
Yes, sir.
Okay, so you can see the screen also, right?
Yes, sir.
Can you? Yes. Again, today I'm not feeling so good. Okay, but still let us continue. It's only 1 hour class. So, but I will speak less loudly. Okay, it is causing me throat problem. Uh, what is the useful energy that is being that is used for moving the aircraft forward? This can be calculated from the work done or the power required for moving the aircraft forward. Okay, so this is equal to the thrust F, which acts on the engine, multiplied by the velocity of the aircraft in the forward direction or the engine in the forward direction. So thrust into velocity gives us the power, useful power for moving the aircraft forward, which is P, which we denote as PT. Okay, so F into VI. And what is the total energy that was available to us? The total energy that was available to us after the conversion in the engine. Okay, this is the total energy that is available to the exhaust gas, which could have been used in the ideal situation for moving the aircraft forward, is equal to the sum of the useful energy PT, means thrust power, plus the energy which is not useful, which is being lost to the atmosphere. So what is the energy that is being lost to the atmosphere? That is the kinetic energy of the exhaust gases that is not being used. Okay, so if you are a static observer sitting on the ground, okay, as we have seen in the previous class again, I think. If you are a static observer on the ground, did we discuss it? Yes. So from your point of view, say this is the engine. Okay, some engine is there. So I will just use a different color to denote that. Where we'll keep the yesterday's marks also. This is the engine that is moving forward with velocity vi. Okay, and air velocity is 0 outside. Okay, here the air velocity is 0. So to a static observer, the air velocity is 0, engine moves forward with vi. Okay, and someone who is sitting on the engine, he sees that the inlet velocity is vi. Okay, because he is sitting on the engine, with respect to him, the inlet velocity is vi, and with respect to the engine, the exhaust velocity we have calculated as v. Okay, this is all the calculations that we are doing is with respect to the engine. Okay, so to the static observer, the velocity of the exhaust gases from the engine is V minus Vi. Okay, and this velocity, this kinetic energy associated with this velocity, half m dot I into V minus Vi square. Okay, this term. This is nothing. This is not being used. This is just dissipating in the atmosphere. Okay, this extra energy is not being used. This is dissipated in the atmosphere. So this is the unused energy. Okay, so this is the not useful energy. This is the second part of the denominator. Okay, So like this you can define the propulsive efficiency. If you simplify, as we have discussed in the previous class, we find that propulsive efficiency can be written as 2 divided by 1 plus V by Vi. Okay. And we have considered a few cases towards the end of the previous class. What are the cases? If Vi tends to 0, means the velocity of the aircraft is very less, okay, as compared to exhaust velocity. In this case, the propulsive efficiency is almost equal to 0, okay. If Vi is very less, the thrust that the power that is used for moving the aircraft forward is negligible, okay. F dot Vi is negligible. So most of the kinetic energy is lost to the atmosphere, okay. Most of the kinetic energy of the exhaust gas is lost to the atmosphere, and the propulsive efficiency is almost 0, but the thrust is maximum at that point, okay, because thrust is given by what? The thrust is given by m dot into V minus Vi. Because Vi is negligible, the thrust is maximum, okay. We have also seen the opposite case. When V tends to Vi, means Vi is almost equal to V. It cannot be exactly equal to V, but say it is almost equal to V. Okay. The aircraft velocity is just a little less than the exhaust gas velocity. In that case, the thrust will be very less. Okay. V is very near to Vi. So V minus Vi is very small. Thrust will be very less, but the propulsive efficiency is very high. It tends to 1. Okay. Why this is the case? Because the kinetic energy of the exhaust gases, which is lost, the absolute kinetic energy is
That is
minimal.
zero.
Okay, yes, it is minimal. So we get most of the energy that is generated is used for moving the aircraft forward. Okay, and also for alpha equal to half, for which case we get the maximum thrust power, we see that the propulsive efficiency is 2 by 3. Okay, this is just one of the cases. It could have been anything else also. And based on this, we had discussed at the end that I told you also to think about these cases. Okay, when we can use turbojet, turbofan, and turboprop engines. Okay, so we have considered a few cases. I will just repeat again because this part is so important. Okay, so we have considered, say, we have 3 cases. Okay, say we know after calculation that turbojet engine, because of the nature of turbojet engine, for turbojet engine, I am just repeating yesterday's thing again. Okay, so it might feel like repetition. So for turbojet engine, let us say that because of the nature of the engine, because it deals with very high uh, uh, kinetic energy of the exhaust gases, we get exhaust gas velocity relative to the engine. The exhaust gas velocity is 3000 km per hour. Okay, to put some realistic numbers. Okay, for a turbofan engine, let us say that we get around 1200 km per hour exhaust gas velocity relative to the engine. And for a turboprop engine, so let us say that we get a velocity somewhat similar to 700 to 800 km per hour. This is the velocity of the air after the engine. Okay, so why this difference is there? This is because of the nature of the engine. Okay, so for turbojet we have seen that there is just the hot jet. Okay, so if you remember again, so for turbojet, all the exhaust gas goes through the combustion chamber, the turbine and the nozzle, and because this is very hot, this gas after the combustion chamber is very hot, it has lot of energy, enthalpy, so it can be expanded to very high velocity in the nozzle. Okay, so you can get very high velocity in the nozzle. Okay, on the other hand, for turbofan, which we will discuss later anyway, what happens is that some part of the air flows through the combustion chamber and exits at very high velocity. It can be accelerated to very high velocity. Okay, this diagram is more accurate. So instead of this diagram, you can consider this one. So the part which flows through the inner chamber goes through the combustion chamber, becomes heated and goes to the hot nozzle. You can see by the red arrow. Okay. This goes out at very high velocity, similar to turbojet. Say this velocity is also 3000 km per hour. Okay. Then there is also another portion of the air which does not pass through the inner region, which just passes through the outer region. Okay. This air is accelerated only by this big fan. Okay, or couple of fans are present, which accelerates the air to some velocity say around 700, 800 km per hour. Okay. This fan also rotates at high velocity. It accelerates the flow to say 700, 800 km per hour, like a propeller. So the combined velocity, average velocity at the exit, it's somewhere between this 800 km per hour and 3000 km per hour. So because the mass flow rate in the outside section is much more than the mass flow rate in the inside section, okay, around 10 times, the average velocity is not very high. So that is why I have put the average velocity as 1200 km per hour, some typical value. Okay. On the third, say for the third type, the turboprop engine, you have a large propeller. Okay, the exhaust gas does not play much part here. It is only there, like most of the energy that is present is extracted for running the compressor and the propeller. Okay, very less energy is there to be expanded in the nozzle. So the entire air is driven by the propeller. Okay, and the propeller cannot accelerate the flow like a nozzle. Okay, so it can only accelerate the flow to some subsonic velocity because the propeller itself is the tip velocity needs to be lower than the sonic velocity. Okay, otherwise it creates complication in the airflow pattern, turbulence. So as a result, the flow is also not accelerated to sonic velocity, it is in the subsonic region. That is why we have put some value like 800 km per hour, okay, for some approximate value. So based on this, we have discussed that what should be the type of uh, application for each of these aircrafts. Okay, so we have discussed that if we need a aircraft with very high application, okay, say if we need a aircraft with very high velocity, our requirement is such that the aircraft should fly at 2000 km per hour. Okay, then obviously turbofan or turboprop cannot provide this velocity because the exhaust velocity itself is lower than this velocity. And if the exhaust velocity is lower than the aircraft velocity, obviously it cannot generate any thrust. So the only option that is left to us is either turbojet or rocket engine. Okay, for military aircraft, either turbojet and rocket engine. But rocket engine is very inefficient because it needs lot of mass because it needs to carry its own oxidizer with it. Okay, so the only option left to us is turbojet engine. We will come to ramjet and scramjet also, which can also be used, but their nature is also similar. They are in those cases also the exhaust gas velocity is very high. Okay, so in that sense, they also have very high exhaust gas velocity and their propulsive efficiencies are also higher at very high velocity. Okay, so rockets were the other option, but that cannot be used because as I said, they are very inefficient. So rockets are only used in those cases where you don't have any air. The atmosphere is very thin, like for space applications or very like some applications which goes near the outer means outer space region, like very high altitude application or space application. In those cases, you need to use rockets because jet engines cannot work without air. Okay, so this is typically used for military application, but has been used for passenger aircraft, for supersonic passenger aircraft like Concorde. Okay, I think there was another supersonic aircraft also, Russian aircraft. I don't remember the name. If anyone remembers the name, they can tell. But Russia also had one parallel aircraft similar to Concorde, supersonic aircraft, which has also stopped. Okay, working. So typically, most of the long distance passenger aircraft we have discussed. So long and medium distance passenger aircraft. use turbofan engines. Okay, distance passenger aircraft. So typically this type of aircrafts flow just below the speed of sound. Okay, say the average velocity is 900 kilometer per hour, 900 to 1000 kilometer per hour, Mach 0.85, 0.9 around that range. Okay, cruise velocity. They are kept below the speed of sound so that they don't have this sonic boom and very loud noise, all these things. Okay, it is comfortable to fly at this velocity, but you want to go as near to the speed of sound as possible to reduce this flight time. Okay, so this is like optimum value. So in this case, if we use a turbojet engine, what is the problem? We could have used a turbojet engine. Then what are the problems? Can you say couple of problems? Two major problems. If I use a turbojet engine for this case, any answers? Who are there?
Needs a high time for needs a minimum time to record the attain the velocity because we can't attain certain acceleration because of turbojet.
No, that is not correct because this is for long distance flight. You have sufficient distance for attaining the velocity. Okay, so say we are going from here to say some 2000 kilometer far away, means here to Delhi or even farther away. So from here to London. Okay, so I can, and the velocity is not very high, right? Velocity is, can I reduce the size here? Some zoom button is there. Does anyone know how to reduce the zoom of this Microsoft Whiteboard?
Sir, I think here below button has been given, like
Where is it? Here.
the lower tab, sir. You see, pens are there, na different colors. Here only plus and I think minus sign in there. I think this only is for zoom in, zoom out.
No, this is
Just
insert
beside
menu.
of this rotation tools.
Undo, redo,
Oh,
template.
yes.
I will see later. Okay, I will see later.
Or just to use control and scroll button, sir. It will also reduce size and
Ah,
increase.
that should do, right? That should do. Correct. It's going to this value only. It cannot go below that. Okay. I just wanted to look at who is present so that I can ask the question. Okay, so we have said that the speed should be 900 kilometer per hour. Okay, this is not a large speed. We are not trying to go to 2000 kilometer per hour. Why we are not going to 2000 kilometer per hour? I have already said that for passenger aircraft, this is uncomfortable. You have to like this is not uncomfortable. You can, but then you have to go to the sonic speed over non-crowded area or non-residential area. Otherwise, it will create a sonic boom. And so this type of passenger aircraft at very velocity cannot be used because of regulations in many places, like over cities or other places. Remember, military aircrafts also have lot of regulations. If you don't know, military aircrafts cannot go supersonic near large cities. Okay, so they are prohibited to go supersonic at supersonic velocity, means change from sonic to supersonic velocity near large cities. Okay, so whenever they are doing test flights, they go to some other areas. So our speed is comfortable speed is 900 kilometer per hour. So I am saying that for 900 kilometer per hour, which we have already decided as a design parameter, why cannot we use a turbojet engine? Because turbojet will be able to provide the thrust because its exhaust gas velocity is 3000 kilometer per hour. So it will provide lot of thrust. M dot into V minus Vi. So this is Vi, right? These values that I am writing, these are the Vi values. So thrust is M dot into V minus Vi. So because V minus Vi will be large, turbojet will provide lot of thrust in this case. Even better than this military aircraft. Turbojet will provide lot of thrust for the civilian aircraft
Sir,
because Vi is small.
lot of fuel will be wasted, right? if we can get the same amount of thrust using turbofan, in which
Yes.
del V is less, that's better.
Yes, yes, that is true. But from more technical term, can you say means
Propulsive efficiency, sir.
propulsive efficiency will be lower for turbojet, right? That is correct. Propulsive efficiency. Propulsive efficiency is denoted like this, right? So V2 by 1 plus V by Vi. If V by Vi is large, okay, which will be the case for turbojet? Say this value, okay, 3000 by 900. Let us put some numbers here, okay. Let us try to understand. 3000 by 900. What was the other part? 1 plus by 2, something like this, right? Eta P. 2 by 1 plus V by Vi. Okay, so what is the propulsive efficiency in this case? This is, it would have been easier if we had taken it as 1000, but 900 also it is 10 by 3. So 1 plus 10 by 3, okay, 13 by 3.
0.5 or less than 0.5.
Yes, yes. So this is around 10 by 3, 13 by 3, so 6 by 13, okay, less than 0.5. In the other case, if we use a turbofan engine, propulsive efficiency will be 2 by 1 plus 1200 by 900, okay. So this is 4 by 3, so 7 by 3, 6 by 7, okay, very high as compared to turbojet. So although we will be able to generate lot of thrust, okay, and the kinetic energy of the exhaust gases also will be very high, most of it will not be used. Only half of it will be used for propelling the aircraft forward. In this case, you can see more than 85% of the energy will be used for propelling the aircraft forward. Okay, so so you can say that then how is it? Means this is generating more thrust as compared to turbofan, more specific thrust. Okay, per unit mass flow, more specific thrust. Then still, why it is giving means the other case is giving better result. So you have to think
Loss of
in terms.
kinetic energy is more.
Yes. So although it is generating huge amount of thrust, okay, specific thrust, most of it is just getting lost to the atmosphere. Okay. Only small part of it being used, or half of it is being used for moving the aircraft forward. In this case, very less amount is getting lost to the atmosphere. Okay. But the specific thrust is low for this turbofan engine. Okay. So thrust is low, right? V minus Vi is low. So then, well, how can we? So we need a certain amount of thrust. Say our engine is for a large passenger aircraft, say Airbus 380 or something like that, Boeing 747 or Boeing 787, which is a very large aircraft. We need huge amount of thrust so that it can take off and it can fly. So because this thrust is low, specific thrust is low, so what should we do in this case, turbofan engine? V minus Vi is already fixed, right? 1200 minus 900. The only option that is left to us is to increase mass flow rate. That's why you will see in modern engines, the engines have huge size, okay, to increase the mass flow rate. If you compare to old engines, you just go to Wikipedia sometimes and check the old engines and new engines, okay. I don't have a picture, I think, of old turbojet engine. Okay, but turbofan engines nowadays have huge diameters. This is a recent one. I think this is for the Boeing 787 Pratt and Whitney engine. Okay, GE also has Boeing 787 or Boeing 787 engine. So they are taking from two suppliers. These engines are huge in diameter. If you see old turbojet engines, you will see that they are very narrow, thin in nature. Okay, they are very narrow in nature. I don't have a picture, unfortunately. I should have had a picture here. Okay, of a turbojet engine, passenger aircraft with turbojet engine. But you get the idea. Okay.
Sir, I have a question regarding this.
Okay, ask.
Let's say I want to design a passenger aircraft with turbojet,
Yes.
but this propulsive efficiency is the only thing that's worrying me. So I'll just reduce the pressure ratio of the cycle. So the exhaust velocity will reduce, right?
You will reduce, yes, exhaust velocity can be reduced. Correct. Correct.
So my propulsive loss is like the propulsive efficiency will increase in that way, right?
Correct. It's a good point. It's a good point. What you are saying. I understand your question. So say you have a lower pressure ratio. Okay, means across the nozzle. Overall pressure ratio is lowered. So across the, so your exhaust velocity you have reduced even for the turbojet to 1200 kilometer per hour. That you can do. You can design a turbojet with 1200 kilometer per hour exhaust gas velocity. That is your question, right? So why we are not using that instead
Yes,
of
yes.
turbofan? So although here we are just thinking in terms of propulsive efficiency, okay, in general, the efficiency of conversion also means the engine efficiency also actually is better for turbofan in this range. We are not discussing it because my focus here was to show you the effect of propulsive efficiency. Okay, but if you solve some problems later on, you will see that in this velocity range, okay, in this velocity range, the overall efficiency. So we will define. We have not yet defined the overall efficiency. So there is an overall efficiency of the engine, which is multiplication of thermal efficiency and propulsive efficiency. Okay, so this overall efficiency itself is higher for turbofan engine. Okay, so it is better to design turbofan engines. Even if you have turbojet with 1200 kilometer per hour exhaust velocity, the efficiency of the turbofan will be better as compared to turbojet. So there are some curves called characteristics curves. These things will come later on. I don't know whether I have a
Sir,
comparison here or
does that for in case of turbofan, does that the air which is circulating, which is flowing outside from the combustion chamber, from the outer channel,
yes,
that is
yes.
also helping somehow, no, sir, in cooling the engine or something.
No,
Uh,
that is actually not no. Don't think in terms of cooling. Okay, cooling in the turbojet also we can do cooling. Okay,
use, yes,
what
sir.
happens
Yes.
what happens is that some of the air is taken out. I don't, let us see whether I have some slide. Okay, these things we will discuss anyway later. But what happens is that whatever is the air that is coming to the combustion chamber and the turbine from the compressor, some of it is taken out. Means it does not take part in the combustion process. Okay, some of it enters as cooling air in the combustion process. Some of it goes to the turbine blades for cooling the turbine blades. This is known as bleed air. Okay, so this can always be taken out after the compressor. Okay, so it is not that this is taking any part. This turbofan part. Turbofan we will
Okay.
anyway discuss it in details. So because you are asking the questions, I have to jump the steps here. But this is not taking part in the cooling. Okay, but still the overall efficiency is higher because of the nature of the energy conversion. So once you do the calculation, it will become apparent. Okay, it depends on characteristic curves like this. Okay, at what thrust we get better efficiency and better fuel consumption. Okay, so for turbofan, the performance characteristics has better optimum value at lower velocity as compared to turbojet engines. Okay, so we can draw performance characteristics like this, and for turbojet, the optimum values are at higher velocity. Okay, so up to this only I can say at this point, because otherwise you will get more confused. Just assume that for turbojet you get better characteristics, better performance, even for the internal part also, engine also, better energy conversion at very high velocity or very high pressure ratio. For turbofan, for overall lower pressure ratio, you get better energy conversion. Okay, but question was a very valid one. Okay, what was I discussing before that? Can anyone remind me? Uh, I have lost track actually. So yes, I was trying to look for some image if there is a turbojet plane image. Okay, old aircraft. This is a turbojet. Yes, Boeing 707. See these engines. This is a Boeing 707 with turbojet engine. Okay, size of the engines you see, and compared to the size of the engines for modern aircrafts, like I was showing here. Okay, so compare this to this engine size as compared to the aircraft wing. Even compared to the aircraft wing, this looks very tiny, right? Very narrow. So turbojet engine used to be very narrow, and because it needs less mass flow rate. Okay, but turbofan is larger engine. This is actually now I am going off the track here, but there is an important interesting side effect of this. Okay, what was the
Drag,
aircraft that?
drag,
Yes,
drag
no,
actually.
not about the drag, because this larger dimension is not causing too much drag because the air is anyway flowing through it, right? It is not a solid obstacle, right? So even if you have a large cross section, most of the air is flowing through it. So it is not about the drag. So recently there were a few aircraft accidents, right? For one type of Boeing. What was that model? Does anyone remember? Like a
Max
GK question. Boeing Max, what was 737 Max, huh? Or what
737,
was it?
737 Max.
737 Max. Okay. Uh, yes. So this Boeing 737, okay, not the Max, Boeing 737 actually is a very old aircraft. Boeing 737, it was initially developed during 1960s. Okay. See this initial Boeing 737, this is the later part, the first mass in operation. Okay, no, this is an old aircraft. This they are flying in 2007, but this is one of the first mass-produced 737. Okay, I hope you can see this. What type of engine is this?
Turbojet.
This is turbojet. Can you just say based on the size of the engine that this is turbojet? You can
Yes,
say
yes.
it is very
Turbojet.
narrow, right? Okay. So this Boeing 737. Okay, we will finish this class with today with this story only because anyway time is less. We will today we have entirely digressed from the thing, but let us discuss this because this is interesting. Initially, this was developed with at that time turbofans were not there, right? During 1960s, so passenger aircraft of that time were developed with turbojet engines. So Boeing and Airbus, they had different philosophies. The philosophy of Boeing was that because of other reasons at that time, because of stability and other reasons, they used they had the wing very low. Okay, and the wing was attached to a very low point in the fuselage. Fuselage, you know, right? This is known as the fuselage of an aircraft, like the main cylindrical pressure vessel where you are sitting, which is at higher pressure as compared to outside. Okay, and the aircraft wing was attached to a lower point in the fuselage. Okay, so this type of design decisions has to be taken at the very beginning of when you are starting a new design, like you are starting you have come up with the idea of Airbus A380. So all the major design decisions has to be taken at the very initial point. So what will be the number of engines, where will be the wing attached, what will be the overall diameter of the fuselage. Okay, but so based on this, the power requirement, other things will be calculated. Okay, so these things, once these are designed, they cannot be altered. It's very difficult to alter because then you have to basically essentially design a new aircraft. Okay, so what happens if you have a turbojet engine with this type of aircraft? The efficiency obviously nowadays is not very good. In 1960s it was okay, but nowadays you can go for much better engines. So you want to change the engine to turbofan engine. Okay. So all previous aircrafts try to change the engine to turbofan engines. So what was the problem with this is that the turbofan engines have much larger cross-sectional area. Okay. And because the wing is sitting very low, let me see whether I have, there is a picture. Okay, this picture is very nice. See how low the wing is sitting. Okay, this is also Boeing 737, although it is used by NASA. Turbojet itself is almost very near to the ground. So if you assume that a turbofan has to be attached here, you can imagine that it cannot clear the ground clearance. It will touch the ground, right? Is it clear to everyone?
Yes, sir.
Good. So this is a big problem now for Boeing 737, that they want to use turbofan, but there is no ground clearance for that because of the initial design. Now they cannot move the aircraft wing to the top also. Now they can design new aircraft with better wing structure, but it has been designed long back, but they still want to use those aircraft because so many aircraft are there in circulation. So many airlines are using this aircraft. So the only way to increase the efficiency is to move from turbojet to modern turbofan engine. There are other advantages also of moving to modern turbofan engines, because modern turbofan engines have better quality turbine blades with better materials, better super alloys. They can sustain much higher temperature. So overall efficiency will be much higher as compared to these 1960 engines. Okay, if you can replace them by a 1990 or 2000 engine. Okay,
Sir,
but the
is there
main
no possibility, sir, to use the engine above the wing?
uh, it theoretically it is possible to use an engine above the wing. Some designs are there, but it leads to other difficulty related to stability and other aspects. Okay, so typically you don't want. There are a lot of factors. It's actually, aircraft design is very complicated, as you know.
Ah, yes, sir.
So one is that okay, still 7-8 minutes are there, right? Because other students have said that we want to finish the class by 6:30, 4:30. So
Sir,
yes,
I want to ask one more question, sir. These payloads are there, na, sir? Like
correct.
if we go from military aircraft to passenger aircraft,
Yes,
uh, weights will increase, sir, or weight will be less for some aircraft, weights will be
correct,
higher for
correct,
some aircraft.
correct.
How it will impact the efficiency? Because for that things you need more lift now if weight is more.
So that actually efficiency is not does not play too much part. In that case, the mass flow rate is
That's
the more
actually
important.
factor of safety, na, sir, that matters with, because for designing aircraft we use very less factor of safety, so we can't handle much weight. There is a limitation to it, no, sir.
It is
I will come
highly.
to I will come to your question. Let me finish this part. Okay, story. Okay. So what happens if you use the engine upward? It will become unstable. In one way, you can say it will become unstable, and also the exhaust gases will interact with this. It will disrupt the airflow pattern in the stabilizer and other parts. Okay. So you have to put the engine below, and there is no place. So what have they done in that case? Do you know what have they done? They have put
Sir,
turbofans, but
wheels, something size or something.
not much, not much. So
Oh,
737 with turbofans, if you see, so the 737 Max is nothing but 737 new generation, okay, with the turbofan engines. You look at. Oh, let me see. Go to Wikipedia instead of Boeing page, and tell me what is the change that has occurred here. Okay, let me see whether there is a good diagram or not. Can someone tell me what change has occurred here as compared to the turbojet engine that was present here?
The
so
ground
turbine
clearance,
not visible
first.
See, wheels, not much changes occurred. See, wheel distance, and here also wheel distance, you see not much difference is there. Okay, so it is not about the wheels. Aircraft wing also is same position because it's the same Boeing 737. Where is the engine location now? Where was it previously? Directly below the wing? Now where is it? Is it directly below the wing here?
No, no, it's some front,
It
somewhat
is
forward.
much forward, much forward. They have extended this pylon where the engine is attached, and they have put the engine forward. Okay, so that there is more space, so that it is somewhat slanted upward. Here there is no space to put. Ideally, the engine should have been put at this space. Do you understand? Okay, you see this again. Where is this engine? Okay, some part is extending forward, some part is extending backward from the wing. Here, only some part is below the aircraft wing, and most of it is just forward. Okay, so they have done like this. This was their solution. So why these accidents have occurred? Do you know? Anyone knows what has happened?
No, sir.
But some idea you must have. Somebody must have read. What has happened, I will tell. Okay. So means what is the current conclusion? Investigation is still going on. So what exact nature I cannot tell, but what was the issue of the problem? What is the ground root of the problem? Was that the because of this very forward position of this engine, it has affected the stability of the aircraft. Okay, the original, so aircraft needs to be stable. Okay, it is a very tricky situation. Think about the aircraft when it is in flight. Okay, how is the aircraft balanced? It is balanced, it is like a cantilever, like it is balanced on the two wings, basically like a seesaw. Correct. So you have a wing here, and I think we will have to continue this. So say this is the wing. If I see from the top side, okay, say, oh, this diagram is so inaccurate. Say this is the aircraft and this is the wing. Okay, so this entire load is on the wing. Entire load of the aircraft is on the wing. Correct. So if more load is there forward and less load is there backward, there is a tendency of the front side to dip, right? And if more load is there back, there is a tendency of the front side to move upward. Is it clear to everyone?
Gyroscopic effect, maybe.
Not guidance. So just think of it as a balance. Okay, your entire aircraft is hanging on the wing, right? You are pulling the aircraft by the wing. That is the case, right? When it is in flight, the entire
More weight gone front side.
yes. So when you are lifting the entire lift is generated by the wing, right? So as if you are pulling the aircraft by the wing. So if you are holding the aircraft by the wing, if you think about a toy aircraft which you are holding by the wing, okay, and the front side is very heavy and the back side is very light, what will happen to the toy aircraft? It will try to dip forward, means it will try
Yes,
to
sir.
go down the forward direction. So by putting the engine forward, the load balance has gone up, means become more unstable. More weight has come towards the forward direction, forward of the wing. The weight should be equally balanced between the front and the back direction. Okay, somewhat equally balanced. Some of the unbalance can be taken into account. But this was still not an issue because the Boeing software that is there. So what did Boeing do to overcome this? They built a software because nowadays softwares are very advanced. So that automatically whenever there is a chance, it automatically stabilizes. This software automatically stabilizes the flight. If there is any chance of dipping, it 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 undergoes, or it instructs the flaps and the ailerons or whatever are the, means the small structures are there, right, uh, to change the angle so that it again comes back to the stable position. So this was the say role of the software. So the software always keeps the plane stable, and as a result the plane was quite safe. Okay, now as a side effect of this, what has happened that in certain cases when you actually want the plane to dip forward, for some situation, when you actually want the plane to dip forward, okay, because of certain reason, pilot wants it to dip forward, the autopilot was not allowing the pilot to do it. Means autopilot is thinking that it has become unstable, so it wants to go back to that some position. As a result, what has happened is that some feedback reaction has occurred, and it has stalled, the flight has stalled, means it has gone to such an angle that there is no lift is being generated, and the flight has crashed. Okay, so it has a long history behind this. Okay, that's why this, you will see that many of the Boeing 737s has been grounded after a couple of accidents. 2-3 accidents has occurred using Boeing 737. It is, although it has not directly to do with the unstable nature here, it has to do with the software bug, because the software was not allowing the pilot to take control in certain situations. But the software itself was designed to overcome that instability. Okay, because of putting the turbofan engine. So it's like a long story is there, long background history is there to this, because the engine was changed from turbojet to turbofan in Boeing 737. Okay, we'll stop here. Okay, we'll stop here. We have run out of time, but you can read about these things. These are very interesting. I will take 2-3 minutes just to finish this attendance. We will be late by 2-3 minutes. Okay, Bharatram, he has mailed that some interview is going on, I think, some placement. Then Sachin, quickly raise your hands. Okay, Sachin. Sachin is not present. Sanjay is present. Abhishek Anand present. Vikas. Vikas is present. Manthan. Manthan is present. Ajay Kumar. Ajay Kumar Meena.
Present.
Ajay is absent. And Gaurav. Gaurav Kandelwal. Gaurav is also absent. Sachin. Ajay, Gaurav. Then Jishnu is present. Suresh Kumar is present. Ujjwal is present. Shubham Kumar is present. Pushpendu Das is present. Shyam Kumar. Amgot Shyam Kumar. Amgot Shyam Kumar. Not present. Prabhat Kumar Mishra.
Yes, sir.
Please raise your hand before the time. Where is Prabhat Kumar Mishra? He is present. Okay. Kishan Sai is present. Dhruv is absent, I think. Dhruv is absent. Then Venkata is present. Atul is present. Ramcharan present. Suman present. Ashwini Kumar is present. Gaurav Srivastav is present. Gulshan Kumar present. M Pujari, I think I have seen M Pujari present. Nilesh Kumar is present. Chintu Sai present. Sudipto Das, where are you? Sudipto is present. Lokesh is
Yes, sir.
present. Lokesh present. Ankit Soni. Ankit has also left, is it? Ankit is not present in any class. And Shivang Das is present. Okay. So Bharatram, Sachin Kumar, then Ajay Kumar Meena, Gaurav Kandelwal.
Sir, Ajay
Ajay
Kumar
was
Meena is present. Sir,
okay. I have marked you present. Ajay is present. Gaurav Kandelwal absent. Amgot Shyam Kumar, Dhruv Gar, Ankit Soni. Okay. We'll meet on Monday evening 6 p.m. Okay. Remember, Monday evening 6 p.m. extra class is there. Most probably we will have to take extra classes every week. So I'm sorry for that, but this time number of classes has been given very low, and we want to finish the course properly. Okay. So thank you.
Sir, can you upload lecture videos?
Yes, recent ones I have not uploaded. During the weekend I will do. It takes some time to uploading
Okay.
YouTube. Lot of time. Many hours actually, because of slow internet. So
Okay.
I will upload during the weekend.
Sir, CMF video also.
Yes, I will upload during the weekend. Okay.
Okay, sir.
Thank you.